You're watching a Hanford Communities issue briefing, highlighting important environmental cleanup issues at the U.S. Department of Energy's Hanford site in southeastern Washington, issues affecting citizens of the Pacific Northwest and the nation. The Hanford Communities organization was established in 1994 and is comprised of the communities surrounding the Hanford site, forming one voice to advise the Department of Energy on important transition and cleanup issues.
Good afternoon and welcome to the 200 West Pump and Treat. My name is Bob Popolarczyk. I'm the Vice President of the Soil and Groundwater Project for CH2M Hill here, supporting the Department of Energy. We have a little bit of a history here of Hanford and the issue with groundwater, and what a lot of people don't realize is that a lot of the contamination that has gotten into the groundwater here at Hanford is due to purposeful release of contaminants to the ground back in the 40s and 50s when Hanford was an operating facility, and a lot of it, about 450 billion gallons, got put into the ground because at the time they didn't believe it was going to affect the environment. It would just get hung up in the earth. And unfortunately, that was not correct. A lot of that contamination has made it to the groundwater. It came through a number of sources. There were wells that purposefully injected contaminants into the ground. There are things called cribs, which are just big open trenches where water coming out of the process facilities was dumped. And this percolated through the ground and over time has reached the groundwater, which in this area is about 250 to 300 feet below where you're currently standing. And it's created quite an issue, but that's kind of a little bit of a background on how we got to where we did today. So with that, this is a little bit of an overview of the Hanford site, and this is the Columbia River. That is one of the primary things we're in the business of protecting and cleaning up these contaminants so they don't affect the Columbia River. Currently, you're standing in what's called the 200 West area. We're about 5 to 6 miles from the river, depending on which way you go. And we're a couple hundred feet above the elevation of where the river is. As if you remember, I said the groundwater starts about 250 to 300 feet below us. So it's almost at the river level here from the plateau. We actually are, today I'm going to be talking to you about the cleanup effort we've got going on the 200 area plateau. But we also are doing cleanup along the river. I'm going to touch on that a little bit early in this tour, where we've got 5 additional plants. So we have 6 plants total, the one that you're in today, and 5 more along the river. Those are right at the river, cleaning up contamination that was caused during the reactor operations from the 9 reactors that had operated along the river. So with that, here's a little bit of a chart to kind of try to, a little bit of a cartoon to show, depict the contamination that we have. And it's broken into 2 halves. This is, as I said earlier, is along the Columbia River. And what it's depicting is the way the contamination is determined to kind of look, if you will, back in 2012. When we kind of started a lot of this effort, or as we've gotten into it. And this is based on sampling, drilling wells and sampling the wells and getting actual data so that we're able to determine where the contamination is. Contamination along the river is predominantly chrome. It's a hexavalent chromium that came from a chemical that was used in the operation of the reactors to prevent corrosion. It leaked out, got in the ground, and now we have it. The darker colors just represent higher concentrations of the chrome. This is a model that projects out, based on cleaning up with the pump and treats, what it'll look like in 2037. And without, I know it's hard to see any of these numbers, but in general, it'll be away from the river completely, so no additional chrome will be going into the river. And more importantly, it'll be below the drinking water standard, what's left at that time. So at this point in time is roughly when we project that we will be done. Now, based on actual operation, I'm going to talk about that in a minute, we're actually doing better than that. And we think we're going to get the job done sooner because the modeling, scientists and engineers tend to be a conservative lot, and they do conservative modeling, and the actual plants are operating better than the models projected. But I'll talk about that briefly here in a moment. This is the contamination on the Central Plateau. This is directly under you in the 200 West area. This is a depiction of the carbon tetrachloride contamination. The carbon tetrachloride was a chemical used in PFP when they were operating the facility. It was used as a cleaning and degreasing agent, and it was dumped directly into the ground at that time, again, not thinking that it was ever going to get to groundwater. We currently have a plume that's about 5 square miles of carbon tetrachloride, and this is not the only contaminant. As we get further into the tour, I'll show you some of the other information, but there are other co-contaminants: uranium, technetium-99, nitrate, also chrome. But for purposes of display, and also because it's one of the primary contaminants we're focusing on, we just show the carbon tetrachloride here. The colors represent different concentrations. In about 25 years of operation, the plan is to have removed about 95% of the mass of the carbon tetrachloride that's in the ground and reduce it down to a level that's very close to, if not at the drinking water standard, and then the rest would be handled through monitored natural attenuation. This is a little bit of trying to show over the last 5 years with the funding we've gotten through the ARA funding and other things, what we've been able to achieve since 2009. One of the key things in this treatment process is getting capacity to pump the water out of the ground, treat it, and re-inject it into the ground. We have drastically increased the capacity up over 2 billion gallons a year is what this represents in this year, and we'll increase it even more next year. So this is just kind of showing the capacity. It doesn't mean we're operating at that level today, but it shows what the plants can actually do, how much water they can treat and clean. This is also showing a little bit of a chart of how we have done so far in removing hexavalent chromium in pounds, and it shows back in the early 2007-2008 frame, moving a couple 100 pounds, and in 2012 we've removed over 1,000 pounds, and that level will stay probably close to that this year also. So we're getting a lot of contamination out of the ground. To give a perspective on that, with chrome contamination, a grain of the chemical, about the size of a grain of sand or a grain of sugar, will contaminate about 8 gallons of water above the drinking water standard. So just one little grain of sugar, in a sense, dropping into 8 gallons, and it's above the 48 micrograms per liter state drinking water standard. If you think about that, and then you think of how many grains of sugar are in a pound, and then you say, well, you've got 1,200 pounds in 1 year that we've cleaned out, that's a lot of contamination that we've really pulled out, even though the number itself maybe to some people doesn't seem that huge. It's a lot of contamination that's been removed from the system. And this just kind of, I always refer to our pump and treats as a tool. They're just a tool, like a wrench, like a hammer, that you can use to do something with. In this case, we sink a bunch of wells and we pump stuff out of ground. That's not the only way we clean stuff up at Hanford. We use other tools, if you will. And this was just a listing of some of the other systems we use. The 250 feet of vado zone, or excuse me, dirt that's between us, where you're standing, and the groundwater, we refer to as vado zone. And in this area, there has been a lot of contamination of carbon tetrachloride. And we have a soil vapor extraction system that's been operating actually since the late 90s. And it's removed about 80,000 kilograms, which is about 170, 180,000 pounds of carbon tetrachloride from the soil column. So that's all material that never made it to the groundwater. So that's a really good thing, because it gets harder when it gets in the ground to clean it up, and yet we're doing a good job there. We're also doing other testing and other techniques to determine other ways to clean up other chemicals, to either clean them up or to fix them in place. They're not currently fully being utilized, but again, we're looking at other technologies. And so I just kind of wanted to touch on that to say, hey, this is all about pump and treats today, but there's other tools that we're looking at and exploring to start addressing things like the vado zone, which is sort of the next frontier, right? We've dug up soil sites and cleaned them, we're taking buildings down, we're taking care of the groundwater, but if we want the groundwater to stay clean, we've got to address how to deal with the vado zone so more contaminant doesn't eventually make it to the groundwater. So that'll be a big deal next for us. Okay, I mentioned earlier about, on this map over here, kind of our projections to 2037, and I'm just going to touch on this. This is based not on modeling, but on actual sampling. This is in 2009 along what's called H area. And for those of you that are familiar with the Columbia River, it's what's called the Hanford Reach. And it's out where the D area reactors are. There was 2 of them. And then H area. White Bluffs, as a point of reference, is just down here off the picture. It's a wonderful kayak trip if you're ever looking for a great place to kayak. And then just in 2012, and this is representing hotspots, by the way, where there's significant levels of chrome. The drinking water standard is 48 micrograms per liter. These concentration spots were well over 5,000 micrograms per liter, so significantly above the drinking water standard. And really, just in about 3 years now, we've knocked those down, where they're still above the drinking water standard, but significantly reduced. The other thing is we're really at a point where we're claiming that we've stopped the flow of chrome to the river. There are some legacy areas where the water isn't flowing very much. That chrome is still located along the river, so you'll find it, but no new chrome is going to the river. We've pretty effectively pulled the plumes back now. What this is really showing is that our modeling is conservative and the plants are working as or better than designed right now in cleaning up the chrome along the river. And we should easily be able to make the 2037 goal, if not a bit sooner than that, to completely remove the chrome below the aquatic standard to prevent it from going to the river at what's called 10 micrograms per liter. So I'm giving you a lot of information fast. I hope it's okay. If you got any questions, please don't hesitate to ask. I'm going to shift focus now really more to this plant where you're currently at and where we'll be touring here briefly. This plant was turned over to operations to myself and Mr. Barrett here back in June 28th, remember the day well, last year. And we've been in the process since then of bringing the plant up to full operations. It was turned over for operations, but you turn it over and then you run through a series of operational tests to wring out all the systems for a final time, to finish training our operations staff, and to really ramp it up to full production. And we have we're very close to finishing that process. We have this chart here. The main thing probably to look at here is just the orange line or the pink line, which really shows back in last October. The plant was operating at a low range of about 500 gallons a minute. It shut down frequently, which is why these lines dropped down to 0. And Bill and his team have brought the plant up over this last year, where we're now operating continuously above 1,500 gallons a minute with a goal this year of about 19 to 2,000 gallons a minute, which we've already achieved for one 30-day period. We're going to make another one for DOE before the year's out. So the plant's coming up to speed. This plant is designed for 2,500 gallons a minute total. And so in our operating range, it'll be somewhere around 2,400 gallons a minute. You're never at the total operating all the time. I mentioned earlier the plants along the river are designed to take out hexavalent chrome, and that's all they're designed to do. So they're a very simple plant, and this picture here, this cartoon, kind of shows how conceptually how a pump and treat works. And we take water out of the ground through extraction wells that are located based on the modeling and based on a lot of input from our scientists and everything else as to where to put them. It goes through a series of resins which looks like sand, to give you an idea. It strips out the chrome, and then we re-inject it in the ground. So that's how the 5 plants along the river work. They only take out chrome. That's what they're designed to do, but that's the main contaminant we're focused on down there, so that's why. It's a lot more complicated up here. The Plateau has a mixture of chemicals. We have carbon tetrachloride, we have nitrates, we have radioactive contaminants such as technetium-99 and uranium, iodine-129. There is some chrome in the ground and some other metals from all the processing facilities up here on the Plateau. And so this plant that you're standing in was designed to take out many more chemicals, and it requires a much more complicated system. So as we're walking through the plant today, Bill will be showing you some of that stuff, but this is what's called a flow diagram of the system here. And if you just look at the difference, this is the operating system for the river plants. It takes all of this stuff here to remove all the different chemicals. And what we do is we run the water through the plant in what we call series, going through various steps, and each one of those steps takes out a different contaminant of concern. And when we're done, the water meets drinking water standard for all these chemicals at the moment, except for one, and I'll talk about that later. It's re-injected into the ground below drinking water standards. So it's a plant that's been designed in the last really 3 years. It was constructed in the 2 years, and we've been operating it now for just over a year, and we're about ready to finish with our operational test, and so it'll be full operations after that. What we do is we have a series of wells. This is the same plume we kind of show over there that shows the carbon tetrachloride plume, the 5 square miles. This is where you're standing right now. And so what we did is we drilled wells that are 500 feet deep to the bottom of the groundwater, because carbon tetrachloride is heavier than water, so it tends to sink over time. So these wells go all the way down to the basalt. And we have a series of extraction wells. We currently have 18 operating extraction wells. We just drilled 3 more. We're not hooked up to those yet. And we have 14 injection wells. So what you do in this particular case, we've got kind of a nice bullseye plume in a sense. It's an easy one from that standpoint. We put the extraction wells in the middle of the plume and extract water out. And then these blue lines and dots here represent all of our injection wells. So we inject water back into the groundwater, both upstream of the natural flow of the plume, which is towards the river, which is kind of this way, and downstream. And the purpose of that is to kind of create a bowl effect. We literally lower the groundwater by a few feet in the middle of the plume and raise it up along the outside, forcing the contaminants over time towards the middle. So what that will do is one of the key things we want to initially do when we're treating groundwater, before you actually worry about removing contaminants from the ground, is to stop it from flowing towards the river, or stop it from where you want it flowing from. And that's why I said over here, the thing we've done so far is to stop the flow from going to the river where it was. In this case, we're many miles away, but nevertheless, the further away it gets, the harder it is to get. So by putting these in, we're effectively stopping the flow of those contaminants from going to the river. And our current modeling, based on well level indicators and everything else, says that we've actually accomplished that. So it's very close, but I mean, we are getting there. So the system's working again as designed, which is a really good thing, and we're not yet up to full capacity. Did I answer your question on that? Okay, thank you. So just a little bit about the facility, and then I thought we could go ahead and take a tour of it, because that's kind of the fun part. But it is been designed over the last few years, and when DOE asked us to get started on this back in 2010, one of the requirements they had was that it meets a thing called LEED, which is Leadership in Energy and Environmental Design. It's a U.S. Green Building Council standard for really saying how efficiently do you design and build a facility. And when I first heard of LEED, I thought it would be like a lot of things are, where it's how much insulation do you have and all that, but it's much more comprehensive. It says not only how efficiently does a facility operate, but also how did you build it? Did you recycle material? Were you careful not to use things that might be short in supply, if you will? Were you efficient in transportation? And so it's quite a challenging standard to make. And this facility, the bio building that we're going to go into first, was certified as LEED Gold standard. And it's on the wall over here right behind the cameras, but basically it was the first facility within DOE that's an industrial facility to be certified that way. And as far as I know, we're still the only one. So we're kind of proud of that. It's been good. We've also received some other awards, both from the Project Management Institute and also from the Department of Energy, the Secretary of Energy's Award of Achievement. So facility was built collaboratively with the Department of Energy, working with the regulators to get it done in a fairly short time period.
So we're in the Rad Building right now. That's what we refer to it as. And it's a radiological building. This is where we remove technetium-99, which is a fission product, is a remnant of the production days of Hanford. Most of those have resulted from tank leaks over the year, and cribs like we talked about earlier. But currently this facility is removing Tech 99. And you can see these large gray containers right behind us here. Those are filled with a resin that's specifically made for Tech 99. And this concrete slab you're standing on, you can see it's in sections. That's designed for future expansion. Tech 99 is in this area of the site. And over here we have a uranium plume. And we will be in the future putting additional ion exchange vessels in here to treat uranium plumes in the future. So right now, all the water that comes into this building goes through that large tank behind you and goes through these vessels of resin. And resin is more or less a polymer or a plastic bead that is about the consistency of a grain like couscous, and it absorbs all the Tech 99 in the first vessel. And then the second and third vessel of resin are just for backup continual polishing. When we first started up, the first vessel was removing 100% of all the technetium that went into it. And now it's been in service for over a year, and it's still removing over 85% of the technetium. And then the second vessel, of course, removes everything beyond what we can detect. And then the third one is available after that. So we've been in service for over a year, and we don't anticipate to do a resin change out until maybe next summer, maybe longer. So it's been performing very well. This is, generally speaking, like I said, Tech 99 comes into a tank in the building, goes through an ion exchange system, and that removes all the Tech 99. The water still has nitrate in it, and so that goes on to the biological part of the plant that consumes all the nitrate. Some of our wells don't have any radioactivity in them at all, but they do have nitrate. And so all of the wells that go to this plant go through the biological process to have nitrate removed from it. And then, as we talked about, after the nitrate's removed, we do have carbon tet in the water still, and that's removed from by a stripper tower, which is just like you see in a petrochemical plant. You have water that falls into the top of this large vessel, and it's atomized like a shower head almost. And then air flows up and strips off any volatile chemicals like carbon tet. And then that's absorbed onto activated carbon, and that is shipped off site for regeneration, and then it comes back to us. So that's a closed loop system also. If you ever have a chance to go along the river, this is what our vessels look like along the river where we treat chrome. A little bit much smaller than these. Each one of these 4 vessel trains, we call them, treat about 100 gallons a minute, between 100 and 140 gallons a minute. These are designed to treat 400 gallons a minute. And right now, as we're standing, when we walked into the building, you might not have noticed, but you walk by some flow meters right by that large tank, and we're treating over 500 gallons a minute right now in this building for contaminated water. Overall, we're flowing about 1,600 gallons a minute through this plant right now.
So what Bill was describing to you with the building we just came out of, that's our what we refer to as our radiological cleanup building, if you will. And what happens there is any of the radiological contaminants are taken out. I mentioned earlier that there's about 18 wells that we extract groundwater from the ground right now. Of those, about 4 or 5 of them have radioactive contamination. So only 4 or 5 of the wells go through that building. So around 500 gallons a minute, roughly. The rest of it has chemical contaminants like carbon tetrachloride and some chrome and some other constituents like nitrate. And those wells actually come in right here in this long metal support bracket. You see those black pipes. That's all piping coming in from the 30+ miles of piping that we have across the desert to the various wells. And that brings in the rest of the water. So you have, again, just in nominal terms, we'll have about 2,000 gallons a minute coming in through these pipes here, and about 500 from that have been treated for the radiological contamination. So all of that goes into this first set of tanks here, which is really just receiver tanks or mixing tanks, if you will. And then the process begins. These next set of tanks that you see here, the smaller ones, there's actually 4 of them. It's called a fluidized bed reactor. And that's where we actually use biology, microbes, to break down some of the chemical contaminants. And what it is that the biology is that the microbes, they want oxygen, and we put them in an environment that does not have oxygen or not much oxygen. And so when the water comes through that has the nitrate and has carbon tetrachloride, they actually grab the oxygen molecules off of the nitrate and release nitrogen gas, and they break down the carbon tetrachloride, we're actually finding out also to some extent. So the nitrate that's in the ground gets broken down into nitrogen and oxygen in these facilities right here, these fluidized bed reactors. And then the water continues from there. Now this is the full 2,500 gallons a minute when the plant is operating full capacity. It goes through those systems there to take out the nitrate, and it takes out some carbon tetrachloride. It then goes to these blue containers over here. Those are called membrane bioreactors. And what those are giant filters. The bugs that get used up, we refer to them, the biological microbes, as they get used up and spent, if you will, they stay with the water flow, and they go over to those blue containers over there where we have large filters that filter out all the solids, including all those spent microbes. So what happens is the nitrates are removed here, some of the carbon tetrachloride is moved here. Then when it gets into these blue containers over here, some of the metals come out and all of the solids are filtered out. And then the remaining water, I'm going to walk down a little further so we can kind of see it, but just to kind of complete the story, they go through those tall towers over there. So to separate it from the water and make it easier to basically what we call strip it off of the water, we pump the water up to the top of those towers, and it drops down through a series of what almost looks like ping pong balls. Those whole towers are just full of these ping pong balls, and as the water goes around those balls, it becomes a very thin layer. We also pump air in through the bottom of those towers and suck it out through the top, so the air is going up, the water's coming down, and what that does is it allows that carbon tetrachloride to be evaporated or stripped off of the water. So it actually evaporates the carbon tetrachloride as the water's coming down, and then that carbon tetrachloride is in a vapor form. It's taken by a large ventilation system, and we're going to walk right through the middle of it, but it's mainly those silver colored pipes over there. And what it does then is it is taken by large fans, and we run it through these blue containers, which are full of activated carbon. And that carbon captures that vapor carbon tetrachloride, and allows clean air to progress up that tall stack up there. As I mentioned, there's an exhaust system here that takes any of the carbon tetrachloride laden air off of those stripping towers and runs it through the filters. These ventilation systems run to every single system here in the plant, and it takes air off the top of it, because as the process is working, you will get some volatiles, carbon tetrachloride, and some others that come off during a process. So it's a totally enclosed system. Any air that escapes runs through those filters. Any water goes through the plant, so we capture everything. Okay, I mentioned earlier that in those membrane bioreactors, that's where all the spent microbes and other contaminants are filtered down. Those contaminants are pumped into this building, and this is our centrifuge room. And what we do is, through a two-step process, we use some equipment called sludge thickeners to take out a lot of that water and leave a sludge behind, which is pumped to tanks outside. That's a continuous process. It's always operating. That's why it's noisy in here. And it separates out the water and the sludge. The sludge is sent outside for storage till we fill up some tanks. The water is recycled to the front end of the system so that it goes through and gets treated again. That sludge, when we get enough of it, we run batch processes with centrifuges. And these centrifuges just take out more water and leave us with what almost looks like dirt. And that dirt goes outside this facility to silos where lime is added, and then it's put in large containers. We call them environmental disposal, reclamation disposal facility roll-off boxes that you've seen them on trucks or big orange boxes. Those boxes get filled up and then we ship them over to the ERDA facility, the environmental restoration disposal facility, where they're buried, or the material is buried. So that's how we get rid of all the solids, is either through the ERDA facility or through that activated carbon, or the resin. When that is spent, it gets sent to ERDA also. So that's kind of the whole process in a nutshell.
If you would like more information about the environmental cleanup of Hanford, please check out the Department of Energy's website at hanford.gov. Links to other issue briefings are provided on the Hanford Communities webpage. Thank you for joining us today for this issue briefing.